Welcome everyone to another OCP Tap call. This is call number 136. We have today David Zage, who is currently serves as the time architecture lead in Intel's Network and Edge Group, NEX. David brings over 9 years of experience at Intel, focusing his extensive experience and expertise in distributed systems and security on precision time and time-sensitive networking, known as TSN. His work is centered on the co-design of hardware and software synchronization products and pioneering software-defined TSN architecture tailored specifically for edge computing systems. Before joining Intel, David was a principal member of staff at Sandia National Laboratory, where he led significant cybersecurity initiatives. He holds a PhD in computer science from Purdue University and has notably contributed to the academic and industry community with over 20 peer-reviewed publications, multiple patents, an active role on various conference committees. Please join me in warmly welcoming David Zage.
Well, thank you, Ahmad, and thank you for that introduction. And today I will be talking a bit about as Ahmad mentioned, the TCC and TSN, and how we look to actually harness those pieces. I was invited. Hesham reached out to me and asked, "Hey, we focus a lot on some of what we look at in terms of time and precision time, but can we talk a little bit about how we can use TSN and some of the TSN from the end system perspective?" And so that's what I will try to give here. Now, of course, I prefer to have more of a conversation. So at any time, if there are questions, please just feel free to interrupt. I don't really have the presentation up besides the screen up for the people, but please interrupt and ask questions as we go along to make it a little bit more interesting. All right. So kind of the obligatory legal slide, we will put this up here. It has all the things that you can read on there. I'll talk for a few seconds, so it's up there long enough. And of course, many of the views espoused here are mine. They're not necessarily Intel's, but we have this up here. What are we going to look at today? We have the pieces of time coordinated compute of TSN, a deeper look into some of the alphabet soup that TSN tends to be for many people. And then, of course, I know that this topic is near and dear to many people on the call's heart of enabling precision time and how do we verify that. So we will review that, and then, of course, we'll wrap things up. So we'll start with an introduction to time. I always think it's kind of fun to start with a story with why time matters. I apologize if one or two of you on the call have already heard this story, but I will actually ask an audience question. For those in the call besides Ahmad, does anyone know what's actually pictured on the screen on the right-hand side?
Is that a bunch of telephone wires?
Well, that's a good guess, Dan. It's a whole bunch of wires. But the important piece here is that each wire is 11.8 inches long, or around 30 centimeters long. And these are actually wires that were given out by Grace Hopper, who probably is familiar to many of them on the call, during her presentations to engineers and especially to some of the military folk, in helping them to understand each one of these is actually a physical representation or manifestation of a nanosecond. And so she would give these out to the engineers, and then she would have a microsecond or 984 feet of wire brought in and say, this is what 1 microsecond looks like. And because of that, we should hang this on all of our desks, on all the programmers' desks, that we should never throw away microseconds. And I'll paraphrase and say we should never throw away nanoseconds. And I just thought it was a really cool way of being able to help people visualize what a nanosecond really is. So I just think it's a pretty fun little story. Where does that get us to? Well, these nanoseconds are becoming more and more important across a variety of domains. I will tend to focus more on edge domains, but these things are the same for data centers, for large-scale compute, large-scale distributed systems, cyber-physical systems are all beginning to leverage things like converged networks or being able to leverage converged timelines, and so they need to have precision time and deterministic capabilities. All of these pieces here are being driven by the fact that we're seeing that shift towards software-defined, seeing a shift towards AI-driven, and towards the converged secure networks. So as we see various domains being transformed, like industrial, audio-visual, aerospace, what does this mean in terms of compute? And so, here at Intel, we believe that time coordination is really a key element to creating a software-defined and converged network. We want to be able to understand and define what real time is in terms of time coordination. And so here you can see on the kind of the representative graph on the left-hand side, we have an x-axis that shows compute performance, and we have a y-axis that shows the real-time performance. Typically, your traditional OT operations, some of those things are designed to foster and have better real-time performance, will tend to have great real-time performance, but tend to have a lower overall compute performance, and so they tend to be weak in performance compared to modern day compute solutions. Now on the contrary side to that, you have your traditional IT environments that are dynamic, that are fast, that use high performance compute, but these do not necessarily have the latency bounds or the determinism that are needed to really satisfy real-time applications, and in particular, hybrid systems that have both real-time and non-real-time. And so in order to realize some of those transformations we saw on the previous slide of having software-defined, we really think it's the combination of compute and the real-time performance, so it's performance with time in order to provide that determinism of guarantee. How do we see TCC being realized? Well, we need to enable it with precision time coordination. We want to have our platforms have low latency, low jitter, and we need to support the existence of mixed criticality workloads. Now, of course, here you can see that in order to do that, it requires a holistic view of the stack from top to bottom. We have hardware, we have firmware, we have software, and this holistic picture you see on the right-hand side of where we have the software supporting the hardware or utilizing the hardware, you'll see here, on the bottom right-hand side, one important piece of that we are building upon is our connectivity solutions. This provides a set of capabilities to improve the efficiency and the real-time applications by solving some of the jitter and issues associated with jitter. So that brings me back full circle to basically, so we are seeing these common themes for transformations across domains, in particular, the desire to see converged networks, both for utility, but also for the cost benefits. And then to basically be able to support these, we really see that TSN, or time-sensitive networking, is one of those critical foundations to do this. And so this is one of the largest, initiatives in many of the fields, especially for things like industrial. And so time-sensitive networking is definitely gaining traction as we go along. So any questions so far? Okay. In that case, I will continue. So, a quick overview of, why do we care about time-sensitive networking? I mean, obviously, we wanted to enable all of these good things coming in the future, whether it be Industry 4.0, whether it be improvements in some of our data centers and data center functionality. But really what time-sensitive network gives us is the ability to have determinism and provide a quality of service. It is something that's standards-based and standards-backed, so we can all build on it, and we're all building towards the same goal. Being standards-based, it provides the necessary things that we have for interoperability. And the fact that it is being defined out of IEEE, the 802.1 Ethernet standards, this is really can be thought of as a enhancement to standard networking to make things like management simpler. We have the interoperability, coexistence of protocols. We have the convergence of networks, which allows us to be able to save some operating costs. We have a single management functionality as opposed to multiple management functionality, and all of these things begin to support mixed criticality workloads. And so, that's kind of the why, a little bit more deeper into the why behind TSN. And then let's look at a little bit of the TSN alphabet soup. And so I know oftentimes I hear from people that there's all of these letters: QAV, QBV, QBU, QCR, all of these things, and how do I start to make sense of these? What do these mean for me, especially if I'm looking at the end node? And really, these can be bucketed into, at a high level, there are 4 key elements that are being added to the standard Ethernet. The first is time synchronization. And so this is really time synchronization for devices using the packet transfer over an Ethernet. So it's establishing a common understanding of the time and clocks using the medium that you already have. You don't have to add extra hardware, you don't have to add extra software, and it works over distance. The second piece is to provide the capability to coordinate and optimize the scheduling of packets, the transmission of packets through the nodes and all the switches in the network, and to have guarantees at the receiving node. In other words, we want to shape the traffic and ensure predictable delivery. The third piece that's added is increased availability or reliability of the network. Here on the slide, I termed it redundancy. This allows us to make sure that we have the packets that we truly need to get to the end node get there, and then they still have the right amount of robustness and the right amount of determinism. And then finally, given all of this goodness of time sync, traffic shaping, redundancy, we need to be able to actually configure the system and both the end nodes as well as the system at large in order to actually use this to create a TSN stream going from a sender to a receiver. And so I think all of these pieces kind of put together begin to get us there. It's important to note that these provide a common L2 abstraction for all other protocols to use. And so we'll dive a little bit deeper into not all of these standards listed here, because as you can see, there's a lot of them. There's also, if you go to the 802.1 TSN working group, they have a list, I think it's now up to 20 something accepted standards and 14 under work. And then there's even more proposed ones. And so, keeping up with the standards obviously could be a full-time job just there. And typically you pick and choose which ones are useful for your application. So we'll take a quick deeper look into some of the TSN standards, and then also to make sure that we are all using the same vocabulary. I thought we'd go over a few of the key terms that go into TSN: timeliness, real time. So timeliness is just really being done by having things occur at the proper time. And so, if we have something like this where we have a period of, let's say it's a second, and we are trying to have an event happen every second. Now, of course, given the fact that we also have other effects in our system, we can often have things like latency or jitter impact our timeliness. Was there a question? Okay. Latency is just a measure of the time to complete the task. The jitter is the time variation to complete that task. And so here you can see that the lightning bolts, while we were having a desired period of 1 second, being timely in that timeliness of that proper time at 1 second, you can see here that the events due to influences either occurred slightly before or after, so we actually have some jitter in the system. And we'll talk a bit about how some of the protocols help us to avoid this jitter and maintain our timeliness. The second piece is synchronization. As we have talked about previously, and I think it's fairly well known to the folks on the phone, is the synchronization is the coordination of events that operate in a system. Here you want that, say, if you're doing power generation, you want your generation and your transmission and all of these pieces to be coordinated so that way you have the proper transmission of electricity. If you are using robotics or something like that, you want to make sure your movements are synchronized so that way your robotic arms don't hit each other or don't hit someone that's in the lab. So just some basic terms that we are all on the same page, and because many times these terms can get used and kind of used almost interchangeably at times, and so it can make for some confusion. So just to give us a basic grounding of what we will think about in terms of a network, we are going to go with a very high level simplified network overview. And like I said, this will come kind of from the edge or the formerly sometimes IoT type of perspective. But these type of techniques and concepts hold whether or not you are in an edge network or a more traditional network as well. But then simplified overview here, the network, we want to have bounded latency from a sensor reading to actually being able to do an actuator. Oftentimes, if you are looking at industrial control systems or other systems, you will hear the kind of sense, compute, and actuate loop. And here, that's exactly what we're looking at in terms of I want my robot to be able to tell where it is in 3D space. My node there at the top is my doing the compute to determine where it is in space and what its next action is going to be. And then it will forward that command on to the actuator to actually move the robot itself. And then this loop will continue ad nauseum until the activity is done. So the data path there, as can be kind of thought of because of its sense, compute, actuate loop here would be going from the sensor through the edge node and finally back to the actuator and then continue there. So now that we talked a bit about what the general edge node looks like, one of the things here that we can talk a little bit about is 802.1 QCC. And so QCC provides a software model for being able to manage the quality of service across the end nodes here, here being a talker and a listener. It specifies the support of both netconf and yang in order to be able to provide TSN configuration, TSN end station modifications, as well as the data models needed. And so while if you go look at the specification, I think it's now a few hundred pages long. It basically talks about how do we set up our network and how do we do the control. And it has both fully centralized, hybrid, and distributed models. But in essence, what we want to do is we want to have a end station talk to another end station. We want to send, you see here, 500 bytes every 100 milliseconds. And so we want it to arrive in 500 microseconds. And so these are the requirements that we're placing on the TSN stream. And so, excuse me. as part of the QCC specification, we have a configuration entity in the network. Here you have both a CUC and a CNC, so a centralized user configuration entity and a centralized network control. I believe that's what CNC stands for, if I remember correctly. Of course, it escapes me right now. But here you have the two entities that are being used to do the control. And so let me find my mouse. There it is. And so each of the network components will converse with the configuration entity on the network. Now, of course, if you have a very simplistic network, say just a few machines, you as the human might actually play the role of the CNC in order to do the configuration if you have, just say, a few talkers and maybe a single bridge. Now, of course, as you get to more complex networks, especially in some of the industrial settings, the type of manual configuration is not possible. And so that's where the CNC comes from. It's also interesting to note that for some of these specifications, they are descriptive, not necessarily prescriptive. So if you look at configuration, the CUC could actually be incorporated as other parts of the network, whereas the CNC may be a separate entity. So one might be a logical entity in the network, and one may be truly a separate physical box in the network. And so when the talker is able to request to the CNC, I would like to send this type of stream, this type of flow, and have this type of guarantee, the configuration entity will then respond back to the end station on the left-hand side saying, yes, this can be guaranteed. It will then send out configuration information to the hops on the network in between the talker and the listener. And eventually, and it will also send a configuration to the listener. So that way, once all of these are configured correctly, the talker can then begin to actually send a TSN stream across. And so this is really kind of the theory of how you configure the various nodes on your network. And as I had mentioned earlier, one of the pieces that we focus on is really how do we get the edge nodes, so the talker or the listener on those ends, on those streams, to do what we want to do. And so, towards that piece, we're going to go with a very simplified view of an edge node in that we have connectivity solution and we have compute on that node. We want to run multiple instances of software on that edge node. This was less common, but it's becoming much more common in the fact that the edge nodes are becoming much more compute capable. And so we want to run multiple applications that have potentially multiple quality of services. They have different things they need for latency, throughput, jitter, and even power. And all of these share resources. And so we have contention. And so we need to make sure that our compute and our networking resources are aligned correctly. So how do we do that? How do we use TSN to make sure that we can have more than one software talking out of a box to other nodes on the network? Well, we can actually have a few different types of techniques to do communication quality of service. One is that we can look at having things occur on a deadline. So you could imagine saying, I want to send a packet tomorrow at 9 a.m. And we can set up the system, we can set up the connectivity solution to do that. Or we can have it say, we would like to send out a packet every 100 microseconds. And both of these are possible with the TSN extensions to the 802.1. In particular, we have launch time control. We have our time-aware shaper. So if folks have heard, or we heard QBV earlier, so our time-aware shaper is defined in our 802.1 QBV. And of course, we also have frame preemption which is part of QBU and 802.3 BR. So we'll go into these in a little bit more detail, but wanted to give, trying to kind of build from the high level view of TSN is this alphabet soup of standards, and then how do we kind of narrow it down to what is actually interesting for us at the end system. And then the final piece is, so we've talked about, hey, we have deadlines we want to meet. We have potentially cyclic types of traffic that we want to support. And of course, we also need to make sure that we can send enough data, because even if we can hit the deadlines and the cycle times, if we can only send one packet and we need to send 4, that also isn't a viable solution. And so towards being able to support bandwidth, we have what are known as both credit-based shapers, as well as launch time control can also be used here. In our credit-based shapers, we can see things like QAV, which define the true credit-based shaper, as well as there's newer coming standards like QCR, which focus on asynchronous traffic shaping, and they prioritize traffic on a per class and per stream reshaping as opposed to a per queue reshaping. So different technologies can be used depending on the guarantees that are needed. So let's talk a little bit more in detail about each of these. So launch time control is basically where the application, so you can see one of the software pieces here at the top, is able to set the time that a real time frame is going to be sent out. It's important to note that while launch time is not necessarily a official part of the 802.1 standards, it is actually supported by multiple networking devices, and is a really useful tool in the toolbox for being able to do real-time communication and shape that communication in terms of both when things occur, as well as it can even be used, as I mentioned previously, to shape the bandwidth. You could have it to where you launch only at certain times and while certain gates are open. The second piece is the time-aware shaper. So this is 802.1 QBV, and here the operating system, so working in combination with our software, is able to define when real-time traffic is being allowed, and so you're able to classify the traffic in multiple traffic classes, and the time-aware shaper will only allow certain classes of traffic to be transmitted when those windows are open. And so here in this example, we just have 2 traffic classes, a blue and an orange traffic class. And so if we say the blue is the real time, then we know that the real time traffic is being transmitted while the blue window is open, here in like the first, third, and fifth bucket. And then during the other times, the non-real-time traffic, so this might be best effort, or it might be a lesser class or lower class of real-time, is being transmitted. It's important to note that even if you still have real-time frames that are left here when we switch over from the blue to the orange, they will need to wait for the next real-time window to open. And so it's, this is an important thing to understand of how long do I need to open my windows and how much real-time traffic versus other types of traffic do I have. And so, this is one of the things that's still a bit of an art when it comes to TSN is, you need to have some insight into what your traffic profiles look like. And then the third piece here towards being able to have quality of service is, looking at the frame preemption. And so in this case, one of the things that we want to be able to do is have good utilization of both our compute and our network resources. And so typically this means having best effort traffic alongside of our real-time traffic. Now, if our best effort traffic is consuming a large amount of bandwidth, is using jumbo packets, is using things that are, kind of oftentimes the opposite of what you see in kind of control networks, and where you'll see a lot of packets come out in a very regular manner, we need to be able to support the fact that these real-time packets should be able to and will need to be able to interrupt the ongoing traffic. And so, this is really where the OS is able to basically pause the best effort sending of the traffic and insert the real time. So the nice piece here is this is taken care of by the OS. This is more of a ingrained feature to using 802.1 networking, as opposed to where in things like QBV you definitely need to do a little bit more planning, a little bit more tweaking in order to make sure that you have the right schedule and the right traffic flow. So I will pause there for a minute. Are there any questions? All right, like I said, please, if there are questions, please interrupt. It makes it more fun for me, and hopefully, more exciting for the people on the call as well.
David?
Yes.
I do have a question. When you were going through this, you were implying the blue was the real time, but it's the orange, isn't it?
Yes, I mean, so yes, you are correct in that I labeled, sorry, I didn't really pay attention between my two labelings. But yes, the red here is, or the orange here is real time. And in this case, it doesn't really matter which one is which. It's just that I have two traffic classes. So you're correct. If I'm being color consistent, these would be real time. But the important piece here is that only that type of traffic class is able to be sent during that window. So, this might be best effort on the first box, and box number 2 might be the real time. And they don't, and as we'll see in one of the coming slides, they don't have to be the same length. They can be very different. Oftentimes we'll have other things in there like guard bands and things. But yes, you are correct.
Okay, thanks.
Well, thank you, Steve. Any other questions? Great. So, one of the things that is very important is the fact that we need, as we have real-time applications, we need to be able to classify the traffic, and we need to say, hey, this traffic is more important, is real time than best effort traffic, right? So as a silly example, this traffic is more important than my Netflix streaming. While I know Netflix might be super important at times, if you're in for whatever reason, a large corporate network, other traffic is probably more important than, say, video streaming traffic. And so we need that technique for our application to be able to tell the operating system, hey, this is important traffic. And so, when we create an application, we're using sockets, we can use the set socket options to actually set the socket priority to, basically be a number between 0 through 7, where 7 is the highest priority, and then technically 1 is the lowest. By the way, the VLAN tags and PCP values work. 0 is actually higher than 1, but that's more of a trivia fact than a set in stone rule. And so as part of using the 802.1q standards, an important part of this here is the ability to use the VLAN PCP tags in order to be able to classify the traffic. And so you can see on the bottom right-hand side, we're actually using IP-Link from the IP route tool suite in order to set the socket priority of 7 to the VLAN PCP value of 7. So here we're saying that that socket priority has the highest priority traffic on the network, and then all of the rest of my socket priority values are set to 1. So basically they're set to being equal or to the lowest priority here. And so that's just the way to be able to tag the traffic and be able to have the operating system begin to understand which is my high priority traffic, which is my low priority traffic. So how do we actually then once it's tagged, how do we actually start to use that? And so, this is where, we're talking here about, you can see at the top, time-aware queues. And so TA prio, so this is, the implementation or the actual realization of QBV, and being able to use this to be able to support time-sensitive traffic and being able to support real-time versus non-real-time traffic. And to do that, we are splitting the traffic here into multiple queues, and each of these queues will be scheduled to be open or closed at different times. And so on the right-hand side, we can see here we have our TC command, and we are actually supporting here 8 different traffic classes. And then the very first here line after the number of traffic classes, we are actually looking to support a mapping of, this is the mapping of the socket priority to the traffic class. And we then are able to map each traffic class to a queue that is located in the hardware of the NIC. The queues here are designed, I mean, it's an interesting syntax, but basically what this says is that traffic class 0 gets a 1 queue at offset 0, and traffic class 1 gets 1 queue at offset 1. And so basically you have a number of queues and offset set of values there, not necessarily assigning the queues at that location. So it can be a little tricky the first few times you create and set up TC commands, but this is one of the things you kind of just get the hang of with TC. And as one of my other colleagues at work has told me, that this slide can either take 2 minutes or can take 25, depending on the number of TA prio questions you get. But the other important pieces of this command here are the fact that we're actually scheduling our gates to be open. And so basically what this says here is that my gate for traffic class 0 will be open for 100,000 microseconds, and my rest of my gates will be open for the following 900,000 microseconds. And so basically we have high priority traffic happening once 1/10 of the time at the beginning of a cycle, and the cycle here is is basically the combination of the 2 scheduled entries combined. So we have a 1 millisecond cycle time, and then at the beginning of that cycle, for every cycle, we have traffic class 0 being sent out, and then the gate is closed. And then for the rest of the cycle, we have the rest of the traffic classes being sent out. And in terms of those traffic classes, they'll be selected, based on round robin for the queue, as well as if there's nothing to send, then of course we'll wait there. And of course, the last piece here that you see with the flags is basically saying that the gate control list is being offloaded to the actual NIC in order to ease the burden on the operating system and on the system. And this is transparent to both the user and the kernel. And so, this is how you set up a talker on one side. And so this will then, you will have an appropriately listener on the other side in order to receive the traffic. And the TC commands here are, kind of through the QDisk framework for that it's supported on, and these are your typical Linux commands. One other kind of just a realization of some of the pieces we talked about. One of the things that I think is actually a really interesting technology, and like I said, it's not necessarily part of the official TSN standards, but we use it in conjunction a lot with TSN, is launch time, and being able to do what's often called a TX time per frame, or using the earliest time first queues. Basically, we want to specify when to send per frame. And so in order to do this, we set once again, we use the socket options in the application to tell, hey, we're going to use SOTX time or launch time per frame. And then we place the TX time in the ancillary data. I know it's a little bit, good old C code there, but basically you put the TX time in the header, and the ETF queuing discipline is able to, offload that to the hardware and be able to use that. There are also, software-based versions for this, but of course they take a little bit more overhead. I'm not quite as low jitter as hardware offloads. And these are combined with either the credit-based shaping or the time-aware shapers. So we talked so that was a good amount of talking about some of the TX technology. So we talked there about QBV. We talked a bit about QBU, QBR in terms of the being able to do the interrupting of the packets, and then we talked a bit about the launch time. There are also pieces that relate to the receive timeliness, and so how do we do receive quality of service? Obviously we can do similar to what we do for our TX traffic, in that we marked our TX traffic in terms of its priority. The same thing can be done on the receive side, is mark desired frames, which are the priority, and make sure they are placed in the right queues. We can do pattern matching on the actual hardware itself in order to redirect into the right flows. And then depending on the system, we have things like DDIO, which allow the NIC to directly place packets directly in cache in order to minimize some of the memory contention. All right, so basically, kind of to build on that last slide, how do we in Linux, how do we get the data from when it hits the NIC into actually using an application? And so the first, kind of as mentioned before, we can do prioritization and redirection based on the hardware. And so that here is the MAC filtering. We have the hardware redirected or hardware assisted redirection. Basically, here the key is we want to make sure that we handle the real-time packets first, and they get sent to the right application, and we can redirect to these queues that are mapped to the software. And so, our best effort traffic will redirect. Typically, your best effort applications use AF packet or your standard Linux stack. And we also, look to explore the use of both the kernel fast track stack in terms of AFXDP, as well as user space, low latency, and jitter processing via the DPDK framework. Each of these has its pros and cons. AFXDP is well supported in our community, or in the TSN and real-time community. Intel itself has been supporting the AFXDP and integrating many of the TSN features and many of the advanced features, such as some of the launch time features into AFXDP. DPDK also provides the ability to do a little bit more customization on the user space side. And in order to give people a very, very brief comparison of those network stacks, you can kind of see here on the left-hand side is the standard Linux networking stack. One of the reasons why is a real-time application will have a much higher jitter, have a much higher uncertainty to it, is there is a lot of kernel stack in between the Ethernet controller and the user space. If we talk about AFXDP zero copy, you are short-circuiting the kernel, and in terms of using XDP and eBPF in order to place the packets to the right application with a lot less kernel infrastructure. And then DPDK is also similar in that you bypass completely the kernel, assigning the Ethernet controller, typically via VFIO, to the DPTK application. And so the two software stacks on the right-hand side, the AFXDP zero copy and DPTK, are what we commonly see for using commodity hardware and Linux-based systems in order to enable TSN systems. So I know that many folks in here know about enabling time sync, but I wanted to just make sure that we covered a few interesting tidbits. But I will pause there if there are any questions on the previous section. Okay. So enabling and verifying precision time. I think we're all well aware of PTP, and so typically, as we saw from the standards listed there, one of the blocks that TSN brings to our network is time synchronization, especially packet-based time synchronization, and this is 1588.802.1 AS. The time synchronization supports multiple GMs, particularly via the BMCA algorithm, in selecting the best clock. And of importance to us, especially as we move towards those converged networks and move to some of the things like the Industry 4.0 and other advanced usages, is the multiple time domains. Typically working clocks and global time. And then, of course, as we have these critical systems are being coalesced together, we need to make sure that they have the required amount of redundancy. And so you're looking at hot standby. So,
David,
yeah.
Since there's so few questions, I'd have to help you out. But when on the first one, 802.1as is 1588. Those aren't different things, correct?
Yes, correct. 802.1as is a profile of 1588.
Thanks.
Yeah. No, thank you, Greg. Good clarification. Thank you. So, looking at end station synchronization, how do we make sure that the time is coming into the NIC, and how do we get it, effectively up to the software stack? I know many people have probably heard the word PCIe and PTM many, many times. I know Kevin Stanton has presented that here before, so I won't belabor that point, but we have time coming into the NIC. The NIC and the SoC must both support PTM, but PTM is really one of the critical things we see as an enabler for the next generation of TSN and time-aware applications. The SoCs, PCI bridge and root complex need to be able to support this, and that's one of the things that time coordinated compute has ensured, is that we make sure that the time is able to traverse correctly from the NIC up through the CPU. And then finally, we have to have the right abstractions in our operating system. And in particular here, this is, clock TI, clock real time, but also as we move to multiple clock domains, we look both at, how do we make sure we leverage V clocks and application clocks in order to provide working clocks and global time. And then, of course, we have, P2P4L is what brings time in from the network to the NIC. And then we have PHC to sys from the OS to the NIC. And then, of course, just to reiterate, the importance of making sure we have the right building blocks. This is the, what happens when you run PHC to sys with and without, PTM. You can see here the green arrow is with PTM and the red arrow is without. And obviously we want our errors to look like the green arrow, not the red arrow. And obviously one of the questions becomes okay, so we've talked about TSN. We know that time sync is important to TSN. how do we make sure that we verify that TSN and the time sync are working as we think they are? Well, that comes into being able to have a pulse per second or a hardware mechanism in order to validate and verify that our ground truth timing is what we think it is. And so, we want to be able to validate things like NIC to NIC across the network, NIC to CPU, between CPUs, and even between, being able to eventually capture events based on things that happen across the network. I'm happy to say that Intel timed I/O, oftentimes we talk about TGP I/O, but if you look in the kernel, it's known as timed I/O, has upstream support for beginning in the Linux kernel 6.15, and this is a PPS output of 1 hertz, so a pulse per second. So I think it's great. Please check that out, as well as if you have interest or usages for further pulse per second, both in or out, please contact myself or Chris Hall. In the fact that one of the things that we often have difficulty with is upstreaming this. One of the cool things I thought I would just kind of flash up briefly is this is what a pulse per second looks like when it's captured on a scope. The fun thing here is that this is using an Intel Xeon processor and using a E830 NIC, which was just released a month or two ago. And so these are kind of larger, almost data center-esque NICs in order, and so they have the PCC functionality for doing many of things. While 830 is not designed for TSN, they do provide things like precision time, pulse per second, launch time, and a few of these other features that make them very amenable to real-time applications in other settings. So just, wrapping up. So in conclusion, we have time-coordinated compute. It's our effort to make sure that we have a holistic solution to enable real-time workloads across domains. And I just picked. Can you guys still hear me?
We can hear you. We just can't see your screen.
Yeah, Zoom just said we stopped sharing for you. Give me 1 second.
Yeah, we see your face, but not your slides. So.
Thanks, Zoom. Well, I was on my last slide, so I guess that's a good thing. Give me 1 second. And there. Okay, that should be back to sharing. So
Yep,
time-coordinated compute. Awesome, great. Time-coordinated compute gets us what we need for real time across a set of domains, whether that be seeing Pro AV, so all the things on a sound stage of a modern concert, to industrial, to what's in your aircraft, to even what's going in your data centers. And then your time-sensitive networking is a set of standards that we incorporate as part of time-coordinated compute that allow us to support that mixed criticality workload. Obviously, as you saw, there are an alphabet soup of different standards that can be used to provide the latency, determinism, and jitter that you might want to see. Typically, we focus on some of the UBV, so the time-aware shaping, especially for some of the edge and end systems. There's a lot of great functionality you can use out of there, and of course, just to make sure that people have things to read and help to put them asleep. I've listed a whole bunch of various reading materials here in terms of joint work in defining, what a time-sensitive system looks like in different industries. You can take a look at our time-coordinated users guide. There's some various technical papers on PTM, using PTM in the last piece, as well as we have other things like, the real-time RTC test bench and the clock manager service to help manage time on your system, and of course the real-time at the edge. So I know typically these are shared later, so you can click on the links and then have bedtime reading to help you fall asleep. Thank you very much for your attention, and then I will just open it up to any questions. Or, if you have comments or would like to collaborate on any of these topics, please let me know.
David, the telecom guys are working on network slicing. Are they using the same IEEE standards that TSN uses, or is it completely different?
They use the same standards. They have kind of, as Greg had mentioned, like similar things like 802.1 AS has its own, is a profile. They have a 802.1, I believe it's deep. There are also telecom kind of specific standards there that define things like the latency, the delay and jitter that are acceptable, but they use the same TSN standards. That's the whole goal, right? Is so that way we can at least build most of the wheels once and not have to rebuild them.
Okay, thanks.
Great.
So David, in one of the previous Intel presentations, we talked about Python and precise time. Has there been any more work related to that, or that's still in progress?
That's still a work in progress.
Okay, thanks.
Yep. I mean, and Daniel, to be honest, there one of the things that we would like to see is we need to figure out where it goes, and typically we need a code traveler to help us upstream it. And so right now we need to figure out who that code traveler is.
Thank you.
Yep, no problem.
All right, yeah, I think that's a feature everyone is looking for, David. So let's put some emphasis on it.
Okay, yeah, and I'd definitely be happy to explore a little bit further with you as well.
For sure, for sure. All right, no more questions.
Stunned silence.
Right. Okay, hearing none, we'll consider that an adjourn, and thank you again, David, for your fantastic talk, and looking forward to see everyone in 2 weeks. I think we have a talk by Pat, if I'm not mistaken, about BPS. All right, we'll see everyone in 2 weeks.
Thanks, David.
Thank you,
Thanks,
David.
everyone.
Bye.